Hi and hello to everyone. In this video, we are going to see about the basic concepts in operational amplifier. Operational amplifier is a very important IC, integrated circuit in analog electronics. I can say you can do any application by just using a single operational amplifier. In this video, we are going to look at the definition of Opamp, equivalent circuit of Opamp, practical and ideal characteristic of Opamp, and how an op-amp is used in open loop mode of operation. Welcome to the lecture. First, we'll see what is an op-amp. There are so many varieties of op-amps are available in the market. For educational purpose, the most widely used op-amp is op-amp IC741. Op-amp comes in different packages. We know any IC can be packaged. So this is the op-amp we use. This is an 8-pin DAP, that is dual inline package. Okay, it is an 8-pin. And this is another op-amp, that is op-amp 547, which is coming at dual inline package surface mount technology, SMT. We can see all the 8 pins are in one side. This is another op-amp. This is TO5 metal can. This op-amp has a metal can and has 8 leads. Okay, 8 legs we have around the metal can. This op-amp is also some IC741. This is also not IC, this is a metal can 741, right? So op-amp comes in different packaging types. It can be either in DAP package, it can be either in SMT package, it can be either in metal can package. Okay, but the concept behind it is always the same. So in our laboratory or our educational point of view, we'll be concentrating on IC741 for all the pin diagram, everything. But the concept you learned can be extended to any of the op-amp. Okay, fine. This is the pin diagram of IC741. Okay, this is for the op-amp IC741. Right, as I said, you have an 8 pins here and we have a notch here. Okay, that is the notch. If you see the IC of the top view, this is a notch here, right? So from here we will be counting from the left side of the notch, we'll be counting the pins 1 to 4. From here we will 5, 6, 7, 8. Okay, the pin descriptions are clearly given. 1 and 5 are offset null. Okay, these pins are very rarely used. This is used to, this is used to, I can say, like tune the op-amp to offset the unwanted voltage or current which is going to develop inside the op-amp in due course of usage, right? But as of you know that this 1 and 5 we are going to use rarely. Okay, right? Okay, then the second pin, is going to the minus terminal, so we say it is an inverting input, and the third pin is going to the plus terminal. We say it is non-inverting. Minus for inverting, plus for non-inverting, and this is the output. And we have two power supplies we have to give, and that is positive VCC at the pin 7 and minus VCC at the pin 4. And the pin 8 we don't have any connection, so we can just simply leave it out. Okay, so this is the circuit, or I can say simple representation of op-amp. So as I said, we have a minus the inverting terminal, plus for non-inverting terminal, and we can say, I can say that the op-amp is always represented by this triangle to say the two inputs, that is the inverting input, non-inverting input, and output, as well as we have positive power supply and we have the negative power supply, and we can leave these terminals, that's null adjustments. Okay, the pin 1 and 5 can be left out, not required. So this is the symbol of op-amp. Now we go into the definition of op-amp. What is an op-amp? Op-amp is a high gain differential amplifier capable of doing various linear and non-linear operations or applications. Okay, so what do you mean by high gain? So its a gain is very high, very large. Differential amplifier. What is differential amplifier means? The difference between the input signal. What is the input signal? We have the input signal at minus, we have the input signal at plus. At minus we say inverting input, at plus we say non-inverting input. Okay, so the difference between these two input signal is amplified. That's why it is called high gain differential amplifier. capable of doing various linear and non-linear operations, or else you can say non-linear applications. What is linear operation? We know addition, subtraction, integration, differentiation, and you can list it out, right? So many applications, right? Okay, these are only few I have given, right, etc. These are linear. What about non-linear? Non-linear is nothing but comparator, clipper, clamper, etc. Okay, we will be seeing few of the circuits in the coming classes, right? Now we will be would understand why it is called operational amplifier, right? What are these operations? These are nothing but mathematical operation: addition, subtraction, integration, and differentiation. These operations are done using operational amplifier. Okay, that's why it is called operational amplifier. And remember one thing, we have to be very clear with analog IC and digital IC. Our op amp is an analog IC. This is an analog IC. And we know there are few ICs which are digital IC. If I say IC, you write it here, IC 7400. IC 7400 is, is a NAND gate. NAND gate. IC 7402 is NOR gate. 7404 is, I can say it's a NOT gate. 7408 is AND gate. 7432 is your OR gate. Okay, these are the ICs are coming under digital ICs. Coming under digital ICs. Okay, because the inputs are digital, should be ones and zeros. Then only I can operate these ICs. Ones and zeros means I can say the input can be 5 volt for 1, 0 volt for 0. I have only two levels of output is possible. Such ICs are called digital IC. But our operation amplifier is an analog IC. Okay, why it's an analog IC? Because it can process analog signals. It can process analog signals. What is an analog signal? Which is continuous in time and continuous in amplitude. Okay, yes, that's what I mentioned here. It's an analog IC which is capable of working with analog signal. Analog signals are signal with continuous amplitude and continuous time. Okay, if you look here, what is continuous amplitude and continuous time? We know this axis is your amplitude axis. This is your amplitude axis. This is your time axis. The signal will be continuous continuous in amplitude as well as continuous in time. Such signals are called analog signals. All real world signals are analog signals. I can say light intensity, the air breeze coming from the fan, the atmospheric temperature, the atmospheric pressure, all are analog values. Okay, to work with such analog signal, we need analog IC. One of the essential or important IC is your op-amp or operational amplifier. Okay, right. And one more thing I want to say here, in IC 741, the power supply we are going to use. Okay, you can look here, the power supply we are going to use is plus 12 volt for plus VCC and minus 12 volt for minus VCC. Okay, and it can be like minus 10 or plus 10. So 10 to 12 volt or minus 10 to minus 12 volt is the range I have to give the power supply for the IC 741. There are some ICs, some Opamp 4114. In that series, we need only 5 volt power supply. Okay, 5 volt power supply. So this plus 12 and minus 12 is for IC 741 type of op-amp. Some other op-amp may need only plus 5 volt. Some op-amp may need only minus 5 volt. Okay, depending on the op-amp you are choosing or we are going to analyze, power supply we have to give. Okay, but other things like inverting input, non-inverting input, output terminal, all are same. Okay, there are some op-amp where inside an IC, there will be two op-amps will be there, right? If you see this 8 pin, inside 8 pins, this IC, we have only one op-amp. There are some op-amp where inside a single IC, we will have two op-amps. Okay, so those things we can extend. If you know this basic idea, we can extend our idea knowledge to the whatever type of op-amp is given. Okay, like either 4114 or 547 this or else metal can type, anything you can extend. Okay, now we will see the equivalent circuit of op-amp. Okay, this is the equivalent circuit. Why we go for equivalent circuit, right? Actually, we do not know what is inside the op-amp, right? We know only the pins, 8 pins. That's IC 741. We have 8 pins. What is inside the op-amp? If you think, I have to analyze, for analyzing purpose, I have to say, I have to represent in some equivalent form. Such model is called equivalent circuit of op-amp. Okay, so we know any device will definitely have an input impedance. Okay, that input impedance is Z in. Okay, similarly, the output will have an output impedance. That's your Z out. As I said in the definition of op-amp, it is a high gain differential amplifier. So what is the differential amplifier? I plus and minus to indicate the dependent voltage, plus and minus, and this diamond symbol. Okay, diamond symbol to say it is a dependent voltage source. What is the voltage gain is AOL into VD. What is VD is the differential input voltage. What is differential input voltage? The voltage at the plus terminal minus voltage at the minus terminal. Plus terminal is your non-inverting, minus terminal is your inverting. So VD equal to V2 minus V1. Voltage at the plus terminal is V2, voltage at the minus terminal is V1. Some books may use some notations like here they will using V1, here they will use V2. Always remember that whatever notation VA they will use, VB they will use. Okay, don't worry about that. Just the difference between the plus terminal and the minus terminal. Here plus terminal I have given V2. In minus terminal I have given V1. So V2 minus V1. That is your differential input voltage. Then Zin is the input impedance, Z out is the output impedance. AOL, what is OL? OL stands for open loop gain. Open loop gain. Okay, so this is the equivalent circuit of op-amp. Okay, actually what is inside the op-amp is very highly complicated. We have hundreds of transistors, okay, hundreds of transistors, hundreds of resistors and capacitor, but that's not our problem. We are not going to study what is inside the op-amp. To analyze, to understand and to develop applications, we have to represent what is inside the op-amp by the equivalent circuit. So this is the equivalent circuit. Okay, equivalent circuit is only for studying purpose. Okay, actually we don't have any single impedance or single output impedance, or else we don't have any dependent voltage source inside it, right? We have a very quite complex hundreds of transistors, hundreds of resistors and capacitors inside the op-amp. We are not going to worry about that. We are just going to represent the input impedance by Z in, output impedance by Z out, and the dependent voltage source by AOL into VD, where VD is the differential input voltage. Now we will see. This is I can say this is for the practical. This is for practical op-amp. Practical op-amp. But ideally speaking, ideally we know it's 100% correct, perfect. Perfectly, the op-amp input impedance is infinite. That is, Z in is equal to infinite ohms. Output impedance is 0 ohms. Open loop gain is infinite. Slew rate is infinite. Bandwidth is infinite. Okay, this I know. This, as I said earlier, input impedance is the impedance at the input terminals. That is equal to infinite. Output impedance is 0. Then what about the open loop gain? Open loop gain is nothing but the, we will understand what is open loop. Okay, if you don't have any relation between no feedback from output to input, we say it is an open loop gain. For an op amp, ideally the open loop gain is infinite. AOL is infinite. Slew rate is nothing but to explain easily for you. We know since it is an analog signal, the signal can change very fast. Okay, at high frequency, this is, maybe I can say this is V2 or V1. It is fast changing, very fast, right? But if to read my op amp, that is the rate of change. Slew rate is nothing but rate of change is infinite. That is, op amp can sense even a sudden change in sense sudden change in input. Okay, this is very important, right? Suddenly changing, if you are not able to sense, see, I am teaching very fast. If you should be capable of observing it and reading it very fast. Some students are very bright, means if I say very fast, they will be quickly writing. Some students are having very poor slew rate, that they can understand very slowly, means what they will do. If I say the second sentence, then only they will be writing the first sentence. That's your equal analogy I can give for the slew rate. Then the next is your bandwidth. Bandwidth. What is the bandwidth? Range of frequency. It's infinite. That is, op-amp is going to be operating at the same way from the lowest frequency to the highest frequency. The lowest frequency we know it is 0 hertz. That is your DC. Highest frequency we know very high value. That's your, I can say, some infinite hertz. For all this frequency, it is going to work in the same way. Okay. And you think about it, right? Our human ear is sensible only for audio frequency, right? Up to 3 kilohertz, 300 hertz to 3 kilohertz. Our human ear is going to hear only the audio or noise, from noise or music from 300 hertz to mean 3 kilohertz or 3000 hertz. So this is the audio range of frequency. If you go beyond that, we are not able to hear that. If it is less than that, we are able to hear that. But if you look at your op-amp, it can work with the lowest frequency to highest frequency. So bandwidth is infinite. Okay, but these are ideal. Okay, but practically, if someone is asking what is practical uh, impedance, simply what you can do is, instead of infinite, you can say it is very high in mega ohms range. Instead of output impedance 0, we can say it is 50 ohms, 75 ohms, 100 ohms. Instead of saying infinite, we can say it is 2 lakhs. Instead of infinite, you can say it is 10 power 6. Okay, bandwidth. For open loop, it's we can say it's very large. That's it, right? Okay, so I can write using some other color. Practically, I'm using red color. It is in mega ohms. Practically, instead of infinite, I can say mega ohms. Okay, mega, we know it is 10 power 6. Mega means what? 10 power 6. 1 mega ohms. Instead of 0, we can say it is 50 ohms or 75 ohms output impedance. Open loop gain, I can say it is 2 lakhs. 2 into 10 power 5. Instead of infinite, I practically am saying it is 2 lakhs. This range is going to change for op-amp to op-amp. Okay, for educational purpose, we may have a this value can change. If you go for some applications where we need a very close to infinite or 0 or infinite open loop gain, we have to go for some costlier op-amp. The op-amp we are using in the laboratory is costing around 15 to 20 rupees only. IC 741 is only 20 rupees. But there are some op-amps which is running into thousand rupees, right? Those op-amps will have the characteristic very close to ideal. Okay, open loop gain I can say 2 in 10 power 5. Slew rate is 10 power 6. Bandwidth is very large. So these are the practical values. These are the ideal values. But remember, to solve the circuit, we will be working only with ideal characteristic. Then only we can make an application quite easily. Okay, we can understand the circuit or we can develop the application easily by only taking these ideal characteristics. That is input impedance infinite, output impedance 0, open loop gain infinite, slew rate infinite, bandwidth infinite. Okay, now this is the equivalent model of the op-amp, ideal op-amp. Okay, as I said, input impedance is infinite. How can I represent input impedance? Just by making it as open circuit. Open circuit. Open circuit means that's nothing. Impedance is infinite. If I make a connection like this, so this is open, right? The current flowing is 0 because the impedance of this open circuit is infinite. Okay, so that's why I made Zn equal to infinite means open circuit. Then Z out is 0. 0 means short circuit. So this, what is the impedance between these two dots? It is 0 impedance. Okay, so Z out equal to 0 means I have removed the Z out, I made it a short circuit. Okay, we have to compare this practical op amp with the ideal op amp, and remember we will be, for analyzing purpose we will be analyzing using only ideal op amp. Okay, there is nothing wrong, there is not a big change in result you will get by going for ideal op amp. Okay, so Z out equal to 0 ohms, right? Okay, now we will see the importance of each characteristic. First characteristic, I said that Z in equal to infinite. What does this mean? Input impedance is infinite means when the impedance, okay, understand the difference between impedance and resistance. Resistance is given only by the resistor. Impedance is offered by all resistor, inductor, and capacitor. Okay, this inductor and capacitor are frequency dependent element whose which is offering the resistance. Okay, the resistance offered by the capacitor inductor together is said as impedance. Okay, right. So since the impedance is infinite, input current flowing into the plus terminal, minus terminal, excuse me, plus terminal is the non-inverting input, minus terminal is the inverting input, is 0 amps. The current flowing into the plus terminal and the current flowing into the minus terminal is 0. I plus and is equal to 0, I minus is equal to 0. Oh, look at it. Op amp doesn't consume current. The current flowing into the op amp is 0. So what is the importance of this? Even a small signal source can drive the op amp. Okay, that is the importance of input impedance is infinite, right? Assume you are using some sensor whose output voltage is very small. Like you can say the output voltage is 3, the sensor output voltage is 3 millivolt. Okay, it's a very small value, 3 into 10 power minus 3. If you connect the 3 into 10 power minus 3 sensor to the op amp, definitely you can, that signal will be moving into the op amp without any loss. Okay, right. Next, what about the output impedance is 0? Output impedance is 0 means it acts as an ideal voltage source. Op amp can drive any number of other devices. What is an ideal voltage source? If you're going to go to the laboratory, if you look at the voltage sources, you can see it will clearly mention that 5 volt slash 1 ampere. What is the meaning? Sir, it is only 5 volt. For how much current? 1 ampere. If you are drawing or extracting or consuming more than 1 ampere, it is not anymore 5 volt. Right? You would have seen you are using inverter in your home, right? Inverter output voltage is some fixed value, but 12 volt I think, right? 12 volt DC. For a battery, I'm sorry, I'm not sure about it, right? For a single battery, you will be using a 12 volt battery. So the inverter will be converting the DC to AC, right? So if you are connecting more number of appliances, fan, fridge, AC, what will happen? You will see a voltage drop. Would I experience that while you are turning on your heater, you can see the tube light in your hall will be blinking. When an engine is started by a bus driver, we can see the bulbs will be, well, for a moment it will be turning off and then on, because when you consume more current beyond this 1 ampere, your source cannot be any more 5 volt. Okay, so ideally speaking, to draw an characteristics, so this is a V, this is I. If it is a 5 volt, if it is 5 volt, it should be constant. For whatever current, it should be constant. Okay, this is an ideal voltage source. Practically, the characteristics will look like this. So if I say this is I, this is V, practically it will be slightly decreasing up to some current only. Up to some current only, it will be 5 volt. Beyond that, it will reduce drastically. Okay, right? So here the output voltage impedance is 0 ohms. So I can say op amp is going to function as an ideal voltage source. So you can connect the output to any number of other devices. You can connect the output to any number of other devices. Okay. So that is then another advantage of going for op-amp. Then the third essential characteristic is the open loop gain. AOL is infinite. We know what is gain. Gain is nothing but output voltage by differential input voltage. V out divided by VD. What is VD? V2 minus V1. VD is V2 minus V1. And we said that AOL is infinite. So V out by infinite. Anything by infinite is 0. So V2 minus V1 is equal to 0. So V2 is equal to V1. This concept is called op-amp concept. You have to understand that the voltage at the plus terminal is same as the voltage at the minus terminal. That is, the voltage at the non-inverting input is same as the voltage at the inverting input. Okay, with this in idea in mind only, we can solve any op-amp circuit or we can build any op-amp circuit. Okay, right? First thing, because of infinite input impedance, the current flowing into the op-amp is zero. So even a small signal source can drive the op-amp. And second thing, when the output impedance is 0 ohms, it acts as an ideal voltage source. So op-amp can drive any number of other devices. Then third point, because of open loop gain is infinite, our voltage at the plus terminal and the voltage at the minus terminal are the same, right? Okay, in the next on videos, we will be seeing these other concepts, right? How to build applications. For that, essentially, you should understand these basics, right? Next is op-amp in open loop mode of operation. V out equal to AOL into VD. So this is an output voltage. If you look at this, what is V out? This voltage is equal to AOL into VD. AOL into VD. What is VD? V2 minus V1. Right? So this is an op-amp which we are using in open loop mode. What is open loop mode? Means there is no straight connection between the output and input. Okay, this is called open loop. But you remember all the applications I have listed in linear operation, adder, subtractor, integrator, differentiator, all will be logarithmic amplifier, all will be in closed loop mode, closed loop application, right? We are one open loop mode, we have only very few application. Sorry, I made a mistake there. A clipper, only comparator. Sorry, make a correction here. See, not this only comparator. In open loop mode, you are using only, you can use it as only comparator. We cannot use it as clipper and clamper. Okay. Right? Nonlinear applications. So nonlinear applications can be extremely sorry. Nonlinear applications can be comparator, clipper, and clamper. But in open loop mode, only application possible is comparator. In open loop mode, only application possible is comparator. We will see what is a comparator. As in, if you go by the name, comparator is used to compare two input signals, right? So, as I said earlier, V out is equal to AOL into VD, AOL into what is VD, V2 minus V1, right? So, okay. So, V2 is the voltage at the plus terminal, V1 is the voltage at the minus terminal, right? So, it's infinite. We'll look at two cases. I can say three cases, right? I have mentioned on case one, where V2 is greater than V1. That is, voltage at the non-inverting terminal, the plus terminal is greater than the minus terminal. In that case, V2 minus V1, V2 is greater than V1 means this is positive. So, infinite into positive is plus infinite. Okay. Similarly, in case 2 where V2 is less than V1, okay, so V out is equal to infinite into negative. V2 is less than V1 means inside the bracket it is negative, so it is minus infinite. If they are equal, the case 3 I can say they are 0. Right now, you observe that since output voltage cannot be infinite, because any electronic devices is bounded, output voltage is bounded by the power supply, right? I can give the analogy: the mobile phone you are using a speaker is there. Laptop, you have a speaker. We have a woofer in our home or public address system, large speaker we have, right? But all these speakers are essentially an amplifier. But what is decided? Only the output voltage decided by the power supply. In the mobile phone, the speaker consumes low power supply, so output is low. In the speaker we have in your home, it consumes bit higher power supply, so output is high. So output voltage is decided by the power supply. Okay, so it is not infinite, it gets saturated, or I can say instead of plus infinite, it will be plus V saturation. Instead of minus infinite, it is minus V saturation. Suppose you are using 5 volt means it is plus 5 volt. You are using minus 5 volt as power supply means minus 5 volt. Okay, and remember, if you are using a power supply of plus or minus 12 volt, that is IC Opamp 741, so the output will be maximum output is plus or minus 12 volt. If you are using an Opamp whose output, let me say the Opamp IC 4114, this Opamp has only 5 volt, so the output is 0 to 5 volt. Okay, if you are using 12 volt, the output is minus 12 volt to plus 12 volt. So this is the maximum value that we say as saturation, minus V saturation plus V saturation. Okay, that's what I mentioned, that V saturation is determined by the power supply. Okay, now let us do some open loop application. Right, I'm taking an op amp. Okay, at minus I have given connected 2 volt. This is my V out. This is my V2, or I can simply say V in. Right. So let's build some open up applications. This is V in. This is 2 volt. This is V out. Okay, right. Can you say what will happen? I know that V out is equal to AOL into VD. What is VD? VD is the differential voltage. What is the voltage at the plus terminal? V in. What is the voltage at the minus terminal? 2 volt. So V in minus 2. As I said earlier, open loop gain is very high, infinite. So infinite into V in minus 2. Okay. Now with the input V in is greater than 2. Greater than 2 means V in greater than 2 means this is positive. So it is output is plus infinite, that I can say plus V saturation. Let me say the power supply I am giving is plus 10 volt and minus 10 volt. This is the power supply, right? So the output will be plus 10 volt. Suppose if I give the input voltage V in less than 2 volt, less than 2 volt. In that case, what happens? V in is less than 2 volt. This is negative. So the output is minus infinite or minus V saturation. Or since we are using a power supply of minus 10, the output will be minus 10 volt. So I can say it is a comparator. It is, if the input is greater than 2 volt, output is 10. If the input is less than 2 volt, output is minus 10. So it is comparing. It is comparing the input with 2 volt. When it is greater than 2, it is giving plus 10 volt. When it is less than 2, it is giving minus 10 volt. Okay. Right. So likewise, we can compare. So this is an application of op-amp in open loop. And remember, in open loop mode, the application is very limited. We have only very few application, that is comparative type of application. Only in closed loop, only in closed loop operation, we can build any applications using op-amp. So that infinite gain is going to act as a problem. Okay, because of infinite we can get the output only how many values? Only two values. In open loop mode we have only two value, plus or minus V saturation. Okay. Okay, so in closed loop mode what we are going to do is we are going to compromise the AOL equal to infinite. Compromise the AOL equal to infinite and have finite closed loop gain. Then only we can develop applications, right? Like adding, subtracting, inverting amplifier, non-inverting amplifier, buffer amplifier, integrated differentiator, logarithmic amplifier, anti-logarithmic amplifier. So many applications is possible. Your clipper, clamper, rectifier, so many applications is possible only in what mode of operation? Closed loop operation or closed mode of operation. In open loop, only one application is possible, that is your comparator. Okay, further what we are going to do, we are going to compromise the gain from infinite, that is we are going to reduce the gain from infinite to some finite closed loop gain. Okay, I hope you learn from the structure. I wish you a happy learning. Thanks for listening. Jai Hind.